Everyone's heard of the Battle of the Rhine. Most people know it was one of the final barriers standing between the Allied armies and the heart of Nazi Germany. A wide, fast, cold river, cutting through the landscape like a natural fortress wall. The Germans knew it too. They blew every bridge they could find, demolished them one by one as they retreated, buying time, buying distance, buying anything they could get. And for a while, it worked. The Rhine held. No crossing, no advance. The war on the Western Front ground to a halt at the riverbank. But in the spring of 1945, a group of American combat engineers looked at that river, looked at their equipment, looked at each other, and decided they were going to build a bridge across one of Europe's most powerful rivers in under 12 hours. Not repair one, not modify one, build one, from scratch, across a river that was trying to kill them the entire time. If you've never heard this story, you're about to, and if you think you already know it, stay with me, because the details of what actually happened on the ground, the engineering, the timing, the near disasters, the human cost, are something else entirely. Before we get into it, if this kind of history is what you're here for, the kind that gets into the dirt and the details and doesn't stop at the surface, make sure you're subscribed. There's a lot more where this is coming from. Let's start with the river itself, because you can't understand what these engineers did without understanding what they were up against. The Rhine is not a creek. It's not a stream. At the locations where Allied forces were trying to cross in early 1945, the river was anywhere from 300 to over 500 meters wide in places. The current was strong, unpredictable, and cold enough to kill a man in minutes. The water level fluctuated with snowmelt coming down from the Alps and the Black Forest. Debris floated constantly downstream, entire trees stripped from riverbanks, sections of destroyed boats, wreckage from bombed-out bridges upstream. That debris was not just a nuisance, it was a weapon. A log moving at speed through a swift current could hit a pontoon bridge with enough force to damage or destroy it. Engineers building in the water had to contend with this constantly. The banks themselves were often muddy, difficult to stage equipment on, and in many locations still under observation or direct fire from the eastern bank. Even when German resistance had pulled back, there were artillery positions that could reach the crossing sites. The Luftwaffe, though severely degraded by this point in the war, still launched strikes against Rhine crossing operations, and the Germans had saboteurs and remaining infantry elements trying to delay, disrupt, and destroy any bridging effort. This was not a construction job. It was a construction job being performed inside a battle. Now let's talk about the engineers themselves, because there's a tendency in histories of World War II to focus almost entirely on the infantry, the tankers, the airmen, and to treat the engineers as support. Background figures who built things so the real soldiers could fight. That framing misses something fundamental. The combat engineers at the Rhine were not in the rear. They were not safely behind the lines stringing wire or digging latrines. They were in the water. They were on the boats. They were working with their hands in a river under artillery fire, building something extraordinary while people were actively trying to kill them. The units involved in the major Rhine crossing bridging operations included engineers from the United States Army's 1st, 3rd, 7th, and 9th Armies, depending on the crossing site. These men were trained specifically for this kind of work. Heavy pontoon bridging, floating treadway bridging, Bailey bridging. The techniques were different, the materials were different, but the core challenge was the same. Get a structure capable of bearing the weight of tanks, trucks, artillery, and thousands of marching troops across a fast-moving river. Do it fast enough to matter tactically, and do it while staying alive. The specific bridge we're going to spend most of our time on was built by engineers of the United States Army, working under extreme time pressure, facing one of the most demanding engineering challenges of the entire European campaign. It was a treadway pontoon bridge, and it went up in 11 hours. To appreciate that number, you need to understand what a treadway pontoon bridge actually is and what it takes to build one. A treadway pontoon bridge is a floating bridge. It doesn't rest on piers driven into the riverbed. It floats on the surface, supported by a series of inflatable rubber pontoons or pneumatic floats arranged in sequence across the water. On top of those pontoons, metal treadway sections are laid, forming the actual roadway. The treadway has 2 parallel lanes of metal decking, wide enough for military vehicles, and the whole assembly is anchored against the current using cables, anchors, and in some cases, powered assault boats that hold the structure in place. On paper, the system is elegant. Each component is designed to be portable, to be moved by truck, to be assembled by relatively small teams, without heavy cranes or fixed foundations. The engineers trained on these systems in England, in France, in every piece of quiet water they could find before they hit the Rhine. But the Rhine was not quiet water, and the scale was unlike anything they had practiced. Each pontoon section weighed hundreds of pounds. Moving them from the trucks to the water required teams of men working in coordinated groups, often in the dark, often while artillery rounds were landing close enough to shake the ground. The treadway panels had to be connected precisely. The anchoring cables had to be set at exactly the right angles to hold the structure against the current without pulling it apart. Every connection had to be right. Every pontoon had to be sealed. Any mistake didn't just slow the job down. It could send the whole bridge drifting downstream in pieces. And the entire time the clock was running. Not a metaphorical clock, a literal, tactical clock. On the other side of that river were American infantry units that had crossed in assault boats, small, flat-bottomed craft that could carry maybe a dozen men at a time. They were across, they were fighting, they were holding a bridgehead, but they couldn't hold it forever without reinforcement, without tanks, without heavy weapons, without the constant flow of ammunition, food, fuel, and medical supplies that an army requires to survive. Every hour the bridge wasn't done was another hour. Those men on the far bank were operating without the weight of armor behind them. Every hour was another hour the Germans had to counterattack, to push back, to throw the bridgehead into the river before the Americans could consolidate. The engineers knew this. The soldiers on the other bank knew this. The generals watching from the command posts knew this. And still, the bridge had to be built correctly, or it would fail under the weight of the first tank that tried to cross. Let's walk through the construction itself. The operation began before first light. That was deliberate. Darkness provided cover from aerial observation and made targeting by German artillery more difficult. But it also made the work harder. The river in the dark is not the same as the river in daylight. Currents that you can read by watching the surface are invisible at night. Obstacles underwater are invisible. The distance to the far bank is impossible to judge by eye. Engineers worked by sound, by feel, by memory of reconnaissance done in daylight hours earlier, and by the faint light they could use without silhouetting themselves against the sky. The first element in any pontoon bridging operation is getting assault boats across to secure the far bank, or, if infantry has already crossed, confirming that the near bank staging area is safe to use. The engineers needed to work from both banks simultaneously, pushing the bridge out from the near side toward the far side, while anchor teams on the far side handled cables and positioned the terminal units that would receive the bridge at its destination. Trucks rolled down to the riverbank. Engineers unloaded pontoons. The inflation of each pontoon took time and manpower. Getting the heavy rubber float down the muddy bank into the water without damaging it required coordination. One slip, one torn section of rubber, and that pontoon was out of service. The engineers had spare components, but every substitution slowed the pace. The treadway panels were brought forward by different truck sections. These were rigid, heavy, unwieldy pieces of metal that had to be manhandled into position. The noise of this work, the clanging metal, the shouted instructions, the roar of engines, all of it was happening within possible earshot and certainly within artillery range of German positions. On at least one occasion during Rhine bridging operations, German artillery found the range. Rounds landed near the staging areas and near the partially completed bridge. Men were killed and wounded. Equipment was damaged, but the work did not stop. Other engineers stepped into the gaps. The wounded were pulled back. The dead were left where they fell, to be recovered later. And the bridge continued to grow out across the water. This is the part that's hardest to convey in a script, or a documentary, or even in a photograph. The simultaneity of it, the violence happening around the edges of the work, while the work itself continued with methodical precision. An engineer connecting treadway sections doesn't stop connecting them because there's an artillery round landing 200 meters upstream. He cannot stop. If he stops, the bridge doesn't get built, and the men on the far bank don't get their tanks. The bridge extended from the near bank outward in sections. Each pontoon was floated out, positioned, and connected to the previous one. The treadway was laid on top as each pontoon was secured. The structure grew incrementally, a few meters at a time, pushed out across the current, while anchor lines were adjusted continuously to keep the whole assembly aligned. Midway across, the current was strongest. This was where the bridge had the most tendency to swing downstream, where the pressure on the anchors was greatest, where the individual pontoon connections were under the most stress. Engineers and assault boats worked alongside the bridge at this point, holding sections in place manually, fending off debris coming downstream, watching for any sign that a connection was working loose. The light grew as the morning came on. That was both good and bad. Good, because the engineers could see what they were doing. Bad, because the Germans could see them too. German observers on high ground or in church steeples could call in artillery with much greater precision in daylight. The engineers were now racing not just against the tactical clock, but against the sun. From the American side, artillery was returning fire on any German gun position that revealed itself by firing on the crossing site. Fighter aircraft were up, looking for German artillery and covering the operation from the air. But none of that could guarantee safety. The crossing sites were active battlefields, and the engineers building the bridge were as much in the fight as any rifleman. As the bridge reached the far bank and was connected at both ends, the engineering teams immediately began checking every connection, every anchor, every pontoon seal. A bridge that looked complete from shore could still fail under load if any element was compromised. The engineers walked the structure, tested the treadway, checked the pontoon heights, adjusted the anchor cables, and then they reported it ready. 11 hours after the first pontoon hit the water. What crossed that bridge in the hours that followed was the weight of an army. Tanks first, the heaviest loads. Sherman tanks rolling across a floating bridge in a swift river, with debris pressing against the pontoons below. Each tank weighed roughly 30 tons. The bridge flexed under that load, the pontoons dipping slightly as the weight moved from one section to the next. Engineers watched from the banks and from boats in the water, ready to act if any section showed signs of failure. The tanks made it across. Then came the trucks, the artillery pieces, the infantry in their vehicles, the ammunition, the fuel, the medical supplies. What had been a trickle of assault boats carrying men one load at a time became a river of American military power flowing east across the Rhine. The Germans could not stop it. They tried. They shelled the bridge. They sent aircraft. They attempted to float mines downstream to damage the pontoons. The engineers and the supporting units dealt with each threat as it came. The bridge took damage. It was repaired. It kept working. What happened at this crossing was repeated at multiple points along the Rhine during the spring of 1945, each one a version of the same story, with different engineers, different specific challenges, different moments of near failure and improvised solution. Taken together, they represent one of the most concentrated displays of combat engineering capability in the history of warfare. But let's go back and give more weight to the individual elements of this operation, because the 11-hour number is remarkable, and it deserves to be broken down properly. The planning for Rhine crossings began months before the actual operations. Engineers at every level, from the Army engineers at the top to the company-level NCOs who would actually be swinging the hammers, studied the river. They had aerial photographs. They had maps. They had hydrographic data about water depths, current speeds, and seasonal flow variations. They had intelligence reports about German defensive positions, including where guns were sighted that could range the likely crossing points. From this planning, the engineers knew before they ever touched the riverbank which sites were most favorable, where the banks were most accessible, where the current was manageable, where German artillery had the least advantageous angles. They pre-positioned their equipment. They organized their truck convoys so that the materials would arrive at the site in the right order for assembly. They assigned specific teams to specific tasks so that when the operation started, there was no confusion about who was doing what. This is the part of military engineering that gets the least attention because it's invisible. The planning, the logistics, the rehearsals. But it's why the bridge got built in 11 hours instead of 3 days, or not at all. The equipment itself was a product of years of development and hard lessons learned in North Africa, in Sicily, in Italy, and across France. The M2 treadway bridge system, which was used extensively in Rhine crossings, had been refined based on combat experience. Earlier versions had weaknesses that were exposed in the field and corrected. By the time American engineers were facing the Rhine, they had equipment that was reliable, modular, and designed to be operated by men who might be exhausted, cold, under fire, and working by feel in the dark. The pneumatic rubber pontoons could be transported deflated, taking up far less space on trucks, and inflated at the site using portable compressors, or in some cases, manually using hand pumps as a backup. The treadway panels were designed to interlock in a way that could be done without specialized tools. The anchor cables and their associated hardware were standardized so that any engineer who had trained on the system could work with any component from any unit's inventory. This standardization seems like a bureaucratic detail. It wasn't. When a unit took casualties and survivors from different teams had to work together on the fly, the fact that the equipment was universal meant they could do it without relearning anything. It kept the pace of construction consistent, even when personnel were shuffled by attrition. The assault boats used to maneuver components into position and to hold sections of the bridge against the current were also critical. These were lightweight metal and rubber craft, powered by outboard motors, operated by engineers who had trained extensively in boat handling. At the Rhine, working these boats was a skill that required reading a fast current, anticipating how debris would move, managing the thrust of the motor against a lateral force, and doing all of it while also physically handling heavy bridge components. The men operating these boats were not passengers. They were active participants in the construction. Let's spend a moment on the debris problem specifically, because it comes up in every account of Rhine bridging operations and it deserves more than a passing mention. As the Rhine crossing operations began in force in March of 1945, the Germans deliberately increased the amount of debris in the river. They destroyed boats, felled trees into the water upstream, and in some areas released floating mines, actual explosive devices designed to drift downstream and impact floating bridges. The debris created two problems. First, physical impact. A large tree trunk or the hull of a wrecked boat hitting a pontoon bridge at river current speed can damage the pontoons, displace the bridge, or in extreme cases snap anchor cables. Second, distraction. Engineers already working at the edge of their endurance had to simultaneously watch the water for debris coming downstream and deal with it before it hit. To handle this, units detailed specific teams to debris clearing. These were engineers in assault boats who worked upstream of the bridge, intercepting large debris items and redirecting them away from the structure. This sounds straightforward. It was not. Getting a boat alongside a large tree trunk, moving at several knots in a strong current, and diverting it without being swamped or losing control of your own craft is genuinely dangerous work. Men were injured doing this. Some went into the water. The Rhine in March is cold enough that immersion can incapacitate a man within minutes. And yet the debris teams kept working, because the alternative was to let the debris hit the bridge, and the bridge was the whole operation. Let's talk about what was happening on the far bank while all of this construction was going on, because the bridge did not exist in isolation. It was the lifeline for an infantry force that had already crossed and was fighting to hold ground. American infantry units typically crossed the Rhine in assault waves using the flat-bottomed storm boats and larger LCVP-style craft where available. The first waves went across without armor, without artillery, with only what they could carry. They established a foothold on the far bank, sometimes under fire from the moment they touched the water. On the far bank, the initial infantry encountered a range of resistance depending on the location. In some areas, German forces had largely withdrawn to prepared defensive lines further east, and the bridgehead was established relatively quickly. In others, particularly where German units were more intact and better led, the infantry faced fierce resistance and had to fight for every meter of ground. The objective in every case was the same: push far enough from the riverbank that German artillery couldn't simply fire directly down onto the crossing site, and hold that ground until the bridge was ready and reinforcements could cross. These infantry soldiers were operating with the knowledge that if the bridge wasn't completed in time, they were on their own. They had radio communication back across the river. They had some artillery support from guns on the western bank. But in terms of armor and the sustained logistical support that keeps an infantry force alive in combat, they were isolated until that bridge went up. The psychological weight of that situation is hard to fully appreciate. Fighting in a bridgehead with a river at your back requires a particular kind of mental toughness. You cannot retreat. There is nowhere to retreat to. The river is behind you. The enemy is in front of you. The only way this situation improves is if the bridge gets built and the armor comes across, or if the Germans manage to push you back into the water. The American infantry at the Rhine crossing points in 1945 generally held under counterattacks, under artillery fire, in some cases under armor, from German tank units trying to seal off the bridgehead, and they held long enough for the bridges to go in. When the tanks finally crossed, when the rumble of 30-ton Shermans came rolling across the pontoon bridge and the infantry could see them coming, that was not just a tactical development. It was a psychological turning point. Suddenly, the calculus of survival changed entirely. You are no longer a small force clinging to a riverbank. You are the leading edge of an army that is now flowing through the gap you created. Now let's go deeper on the engineering specifics. Because the more you know about the actual mechanics of what these men were doing, the more the 11-hour number resonates. The standard M2 treadway bridge used in Rhine operations was designed to handle a load of up to 25 tons moving at a walking pace, which was sufficient for most wheeled vehicles and some lighter armored vehicles. For heavier loads, specifically for the Sherman and the heavier M26 Pershing tanks that were in service by 1945, engineers had to double pontoon sections of the bridge, placing 2 pontoons side by side to increase buoyancy at the points where the heaviest loads would be concentrated. This double pontoon technique added time and complexity to the construction. It also changed the handling characteristics of the bridge in the water, because the wider sections had more drag against the current. The anchoring system had to be adjusted to account for this. Engineers who had rehearsed the standard configuration had to adapt on the fly when the decision was made to beef up the structure for heavier loads. The length of the bridge was determined by the width of the river at the chosen crossing point, plus additional sections to account for the approach angle on both banks. At many Rhine crossing sites, this meant a bridge of 300 meters or more. Each meter of bridge length represented additional time, additional materials, and additional exposure during construction. The anchor cable system for a bridge of this length involved substantial hardware. Steel cables ran from the bridge out to anchors placed upstream on both banks, as well as in some cases to anchored boats that acted as additional anchor points in midstream. Keeping these cables at the right tension was a continuous process throughout the construction. As each new section was added to the bridge, the new weight changed the forces on the anchors, requiring adjustment. Engineers designated specifically as cable tenders monitored this continuously. The connection between individual pontoon sections was made using metal coupling hardware that locked adjacent pontoons together. Alignment was critical. A misaligned connection could put lateral stress on the treadway panels and potentially cause cracking or failure under load. In the dark, working on a wet moving surface, with cold hands and exhausted muscles. Getting these connections precisely aligned required skill that only came from repetition. These were men who had trained on this equipment until they could assemble it in their sleep. And at the Rhine, they came very close to doing exactly that. There's one more element of the construction that deserves attention, and that's the approach roads on both banks. A bridge is useless if vehicles can't reach it. The approach roads to Rhine crossing sites in many locations were damaged or non-existent. German forces had cratered roads, blown culverts, and destroyed any infrastructure that would make accessing the riverbank easy. Engineers had to deal with this in addition to the bridge itself. On the near bank, this often meant bulldozer work to clear a path and stabilize the road surface enough to handle the weight of tank traffic. On the far bank, it meant working in ground that had been recently fought over, potentially under fire, in an area where German booby traps might have been laid. Engineer teams detailed to approach roadwork were operating in a different kind of danger than the bridge teams, but danger nonetheless. When the bridge was declared complete, the approach roads had to be complete too. A tank sitting at the edge of the approach road, because the last 20 meters to the bridge were impassable, was just as useless as no tank at all. Let's talk about the men who built these bridges at a more personal level, because the engineering and logistics are fascinating, but the human story is what makes this meaningful. The combat engineers of the United States Army in World War II came from everywhere. They were farmers from Kansas, and steelworkers from Pittsburgh, and fishermen from Maine, and carpenters from Georgia. Some had prior engineering knowledge or construction experience. Many had none whatsoever before the Army assigned them to engineer units and trained them from scratch. The training was intensive and practical. You learned by doing. You built bridges in training. You operated boats in training. You demolished structures in training. And by the time you reached the theater of operations, you had assembled the equipment enough times that it was in your hands and your body, even if it wasn't always in your head. But training can only take you so far. Nothing in training exactly replicates what it feels like to be on a flat pontoon in the middle of a swift river, while a German artillery shell lands 50 meters away and sends a column of water over you that knocks you off your feet. Nothing in training exactly replicates the weight of exhaustion after 18 hours of physical work under stress. the way your hands stop feeling the components they're supposed to be assembling, the way the simplest mechanical task suddenly requires active concentration because your body is running on fumes. The men who built these bridges were not supermen. They were young men, many of them teenagers, who had been given extraordinary training and were executing it under conditions that would have broken most people. The fact that the bridges went up, that they held, that they performed as designed, is a testament not to some abstract notion of American industrial capability or military doctrine. It is a testament to specific people, with names, who stood in cold water and connected metal sections in the dark, and kept going when the artillery landed near them. It's worth noting that the engineers suffered significant casualties in Rhine crossing operations. These were not safe assignments. The men working on the water and at the riverbank were visible, they were exposed, and the Germans knew exactly what the bridges meant. Destroying a bridge under construction, or even slowing the construction down, was worth a significant expenditure of artillery ammunition and air assets. The engineers on those bridges were priority targets. Despite this, the bridges went in. At Remagen, where the Ludendorff Railroad Bridge was captured intact on March 7, 1945, in a moment of extraordinary fortune and quick thinking by soldiers on the ground, American engineers spent days under continuous German fire, keeping the damaged bridge operational, and building additional pontoon bridges alongside it. The Remagen bridgehead became the first Allied crossing of the Rhine, and it was sustained at enormous cost, with engineers working and dying to keep the crossing points open under German air, artillery, and saboteur attacks. The broader Rhine crossing operations that followed, Operation Plunder in the British and Canadian sector, Operation Varsity with its airborne component, and the American crossings across multiple army fronts, were all supported by engineering efforts that in scale and intensity were unlike anything the war had previously required. Let's look at the broader strategic context of why this mattered so much, because the Rhine crossing was not just a military operation. It was the moment the war in Europe effectively became a question of time rather than outcome. By early March 1945, the situation in Western Europe had shifted dramatically from the dark days of December 1944, when the Germans had launched the Ardennes offensive and briefly put the entire Allied position in doubt. The bulge had been stopped, and the Germans had spent irreplaceable reserves of armor, fuel, and experienced infantry in an operation that failed to achieve any of its strategic objectives. What remained of the German army in the West was retreating, short of everything, fighting rearguard actions to delay what every senior German officer knew was coming. The Rhine was the last natural barrier of significance. Beyond it, the terrain of central Germany offered some defensive possibilities, but nothing comparable to a major river line. Once the Allies were across in force, the German ability to mount a coherent defense became critically dependent on the ability to move reserves, to re-establish lines, to trade space for time. All of that assumed the Germans could keep some order in their forces. They could not. The combination of Allied air power suppressing movement by day, Allied artillery and infantry pressure on the ground, and the growing reality among German soldiers that the war was lost, created conditions for accelerating collapse. Entire divisions surrendered or dissolved. Command and control broke down at the tactical level as communications were disrupted and headquarters were overrun or forced to relocate. The bridges across the Rhine were the physical mechanism through which Allied combat power poured into this collapsing situation. Every hour the bridges were operational. More tanks, more infantry, more artillery, more fuel and ammunition, more everything flowed east. The German rear areas, already under pressure from Soviet advances from the east, began to fracture. The Ruhr industrial region was encircled. The path to Berlin, to the Elbe, to the final surrender, ran through those pontoon bridges. When an American combat engineer connected the last section of a treadway bridge at the Rhine and reported it ready, he wasn't just completing a construction project. He was opening the door to the end of the war in Europe. Now let's address something that doesn't get discussed enough in most accounts of the Rhine crossings, and that's what went wrong. Things went wrong. Things always go wrong in combat operations, and the Rhine crossings were no exception. Some of the problems were mechanical. Pontoons were damaged by debris or by fire before they could be used. Treadway sections arrived at sites damaged from the truck transport over bombed-out French and German roads. Equipment that had been reliable through months of campaigning developed problems at precisely the wrong moments. Some problems were logistical. Supplies that were supposed to arrive at certain times didn't, because the road network was congested with every branch of the army trying to move toward the Rhine simultaneously. Units that expected to have certain equipment on hand when they reached the crossing site found they had to improvise or substitute. Some problems were human. Men were lost, units were disorganized by casualties, officers were killed, and NCOs who had been the practical backbone of operations were suddenly absent. Every unit had plans for succession, but in practice, losing the sergeant who knew the bridging equipment better than anyone else in the company was a different kind of loss than losing the lieutenant whose role could be filled by the next man in line. And some problems were tactical. German resistance in specific locations was stronger than anticipated. Bridgeheads that were supposed to be secure enough to begin bridging operations came under renewed attack and had to be defended rather than used. The dynamic interplay between the infantry fight on the far bank and the engineering effort at the crossing site meant that delays in one directly created pressure in the other. The remarkable thing is not that these problems occurred. The remarkable thing is how they were handled. American combat units in 1945 had developed a culture of adaptation and improvisation that was deeply embedded at every level. When something didn't work, you found something else that did. When the plan was no longer viable, you made a new plan. When the man who knew how to do a thing was dead, someone else figured out how to do it. This is what effective military training and experience produces, not the ability to execute a perfect plan, but the ability to execute an imperfect plan well enough to achieve the objective. At the Rhine, the objective was always the same: get across, get the bridge up, get the armor moving. That objective was achieved, at multiple points, under conditions of extraordinary difficulty, in timelines that were almost too fast to believe. Let's look at some of the specific technical and human moments that have been preserved in accounts from the engineers who were there. One of the most consistent observations in the memoirs and after-action reports of Rhine bridging engineers is the noise. The Rhine crossings were extraordinarily loud. The combination of artillery from both sides, the roar of outboard motors on assault boats, the clang of metal bridge components being dropped and connected, the shouts of engineers coordinating across the noise of the current, and the sporadic crack of small arms fire made communication difficult. Engineers had developed hand signals and communication protocols specifically for noisy environments, but at the Rhine, even those had to be adapted because the sheer volume of sound made it difficult to see clearly enough for signals to be effective. Voice communication in this environment required shouting directly into another man's ear. Radio communications between teams on different parts of the bridge were unreliable because the metallic structure of the bridge itself interfered with radio transmissions. This meant that coordination between the near bank team, the midstream team, and the far bank team sometimes came down to a runner, an engineer in an assault boat, physically ferrying information from one part of the operation to another. This was slow, and in fast-moving construction work, slow communication is a genuine operational problem. Engineers dealt with it by working from the plan and from experience. Each team knew what the team ahead of them was supposed to do. If you couldn't get a message to them, you trusted that they were doing their job. And mostly, they were. Another recurring theme in accounts from Rhine bridging operations is exhaustion. By the time American forces reached the Rhine in force in early March 1945, many of these engineer units had been in continuous operations since the Normandy landings. 9 months of combat, of construction under fire, of building and destroying and building again. They were not fresh. They were functioning on accumulated fatigue, on the knowledge that the end was visible, and on the particular adrenaline-driven focus that comes from having a clear, immediate, impossible-sounding objective. The men who built the Rhine bridges in 11 hours had probably been awake for 20 or more hours before they started. They would stay awake for hours afterward, watching their structure, maintaining it, repairing it, ensuring the crossing continued to flow. Sleep was a luxury that came in fragments, grabbed in the back of a truck or against the hull of an assault boat while another man took your position. The cumulative sleep debt these engineers carried by the time German resistance finally collapsed was extraordinary. And yet, 11 hours. Let's talk about the equipment supply chain that made this possible, because behind the engineers at the riverbank was an entire industrial and logistical system that had been built specifically to support operations like this. The United States Army in World War II built its bridging capability on the foundation of mass production and standardized supply. The M2 treadway bridge components, The rubber pontoons, the steel treadway panels, the coupling hardware, the anchor cables were all produced in enormous quantities in American factories and shipped to Europe through supply lines that stretched from U.S. ports across the Atlantic, through the French port complex, and along the lines of communication to the forward depots. By the spring of 1945, there were sufficient bridging materials in theater to support multiple simultaneous major river crossing operations. This had not been guaranteed. Earlier in the campaign, bridging materials had been scarce, and crossing operations had to be carefully sequenced to avoid running out of components. The logistical buildup that preceded the Rhine operations specifically included pre-positioning of large quantities of bridging materials at locations where they could be rapidly moved to crossing sites when the order was given. The trucks that moved this material were themselves a critical resource. The Red Ball Express and its successor supply systems had been moving enormous quantities of materiel from the ports to the front throughout the campaign, and by early 1945, the supply network had been refined to a level of efficiency that could support simultaneous offensives across a wide front. When engineer units needed their bridging components moved up, those components were there to be moved. This logistical achievement is invisible in the story of the bridges, but it's foundational. The engineers at the riverbank were the visible tip of a supply chain that stretched back thousands of miles to American factories. The 11-hour bridge required not just 11 hours of engineering, it required the entire American industrial and military logistics system working behind it. Now let's situate this specific achievement within the broader story of American military engineering in World War II, because the Rhine bridges didn't come from nowhere. American combat engineers had been building under fire since the campaign in North Africa in 1942. The challenges they faced there, in rugged terrain, against an experienced enemy, with supply lines stretched to their limits, had taught hard lessons that were absorbed into doctrine, equipment, and training. By the time the Army reached Europe for the Italian campaign, and then Normandy, the engineers were better equipped, better trained, and operating within a better organized logistical system than they had been in Africa. The Italian campaign in particular was a crucible for combat engineering. The terrain of central Italy is defined by rivers, narrow valleys, and easily defended ridgelines. American and Allied forces crossed river after river under fire, building bridges, clearing mines, maintaining roads under continuous artillery fire. The Rapido River crossing in January 1944 was a disaster in some respects, a painful lesson in what happens when infantry and engineering coordination breaks down. But even from that disaster came lessons that were incorporated into subsequent planning. By Normandy, the engineer doctrine had been refined to a high degree. The beach obstacles at Omaha, Gold, Sword, Juneau, and Utah were cleared or breached by engineer teams who had trained extensively for exactly this task. The follow-on work of building roads across the Bocage, maintaining supply routes under fire, constructing bridges across the rivers of Normandy and northern France, was performed by a corps of engineers that was operating at a consistently high level. The Rhine, by the standards of what American combat engineers had already done, was the culmination. The biggest river, the most heavily defended, the most consequential, and they were ready for it. There's a detail that comes up repeatedly in accounts of Rhine bridging that I want to spend some time on, and that's the role of the enlisted engineers, the sergeants and corporals and privates, who were the actual hands that built the bridges. American military culture in World War II had a particular kind of relationship between officers and enlisted men that is worth understanding in this context. Officers planned, coordinated, and commanded. NCOs and enlisted men executed. But in combat engineering, the knowledge and skill required to actually assemble the equipment often resided most deeply in experienced NCOs and long-serving enlisted men who had been working with this specific equipment for years. Officers who had been through engineering officer training knew the doctrine and the theory. The sergeant who had been handling M2 treadway components since 1942 knew which coupling hardware tended to bind in cold weather and what you did about it. This meant that in practice, the enlisted engineers had a kind of operational authority that wasn't formally recognized in the chain of command, but was absolutely real in the field. When a sergeant at the Rhine told his lieutenant that a particular approach was going to work and a different one wasn't, the lieutenant who ignored that was going to build a worse bridge than the lieutenant who listened to it. The good officers, the effective ones, knew this and acted accordingly. They set the objective, they coordinated resources, and they trusted the NCOs to make it happen. The bridges that were built in 11 hours were built by partnerships like this. officers who understood the objective and the constraints, and sergeants and privates who understood the equipment and the water. Neither group could have done it alone. Let's turn now to what happened after the bridges went in, because the completion of the bridge wasn't the end of the engineers' work. It was the beginning of the next phase. A pontoon bridge on a major river requires continuous maintenance. The current is constantly working against it. Debris continues to arrive from upstream. The pontoons are subject to wear, to minor impacts, to gradual degradation of the rubber seals. The anchor cables stretch and require retentioning. The treadway panels work loose under the constant traffic of vehicles and require resecuring. All of this maintenance had to be performed by engineers who were simultaneously managing the traffic flow across the bridge, because an unmanaged flow of military vehicles across a pontoon bridge is a recipe for overloading specific sections and causing failure. Engineers controlled the pace of crossings, the spacing between vehicles, the weight categories that were allowed to cross at different times. Heavy tanks might cross at certain intervals with gaps between them. Lighter-wheeled vehicles could be allowed to proceed at closer spacing. This traffic management was not glamorous work, but it was operationally critical. The bridge that had taken 11 hours to build could be destroyed by poor traffic management in minutes if a cluster of heavy tanks arrived simultaneously and overwhelmed a section. At the same time, engineers were already thinking about the next problem. The Rhine crossing was not the end. It was the beginning of the drive into Germany. Every river, every stream, every cratered road, every demolished bridge in the German interior would require engineer work. The Rhine bridges were in some ways the last great set-piece bridging operation. What followed was a rolling campaign of constant, smaller-scale but still technically demanding engineering work at a pace that the engineers maintained until the very last days of the war. There's a moment that several accounts of Rhine bridging record that I want to describe, because it captures something about what these men understood about what they were doing. When the first tanks rolled across a newly completed Rhine pontoon bridge, the engineers who had built it stood on the banks and watched. Not because they were required to, because they wanted to see it. They wanted to see what they had built performing its function. They wanted to see the Sherman tanks, 30 tons each, rolling across the structure they had put in the water in the dark, under artillery fire in 11 hours.